Recording started.
Well, Quality Insulation Installation webinar organized by the City of Chula Vista Office of Sustainability. It is part of our sustainability series, which started earlier in summertime, and it's going to continue until the month of December. Please be aware that the webinar is being recorded. And if you have any questions, please type them at the bottom right of your screen in the Q&A box. Thank you very much. Lynn?
Next slide. Hello, everybody. So we're continuing our development services trainings online, and they will continue through the year. This training will be recorded, so it'll be available to you later. And we have 3 terrific speakers today. Oh, let me tell you about our next trainings coming up. Next slide. So on October 13th, we will have Cal Green Residential Code training. Then on November 17th, the non-residential code for Cal Green. On December 8th, we'll have a training about indoor air quality and ventilation for residential and non-residential. So next slide. We have 3 terrific trainers coming today. Russell King from CalCerts, Rich Williams, and Jeff Adams from Alliance Green Builders, and Danny O'Connell from Next Level Insulation. So since we have just 1 hour for this, and we'd like to also take some questions at the end, which you will put in the chat box, let's get started with Russell King. Take it off, Russ.
Great, thanks. All right, hello everyone. Thank you for inviting me to speak today. We'll be talking about QII and what building inspectors need to know. QII stands for Quality Insulation Installation. Next slide, please. So first of all, a little bit, go back one, please. A little bit about CalCerts, the company that I work for. We are a private company based in Folsom, California. We are approved by the California Energy Commission to be a HERS provider since 2003. We train, certify, and track HERS raters. We are not a government agency. We are not affiliated with, but we're closely regulated by the California Energy Commission. And it's important to understand that HERS raters are not employees of CalCerts. We do have HERS raters on staff. There are QA raters. They basically go around and re-inspect homes after HERS raters have inspected them to make sure that they're doing a good job. And the reason this is all important is because QII is a HERS verified measure. In other words, it's a potentially, it's a energy feature that's potentially required by the Energy Code, but it's been delegated to HERS raters for inspection in the field. Next slide. So what exactly is QII? So QII, as I mentioned, it's Quality Insulation Installation, and it is a protocol for the verification of properly installed insulation. And that's kind of important to understand. It's a verification protocol. It's not an installation protocol, it's a verification protocol. It's based on industry standards. It was not made up by the Energy Commission. It's based on the insulation industry standards from NEMA and ICAA. Those are Insulation Manufacturers Associations. And it's basically how the manufacturers intended for their insulation to be installed. And then the Energy Commission wrote a verification protocol about how to go out in the field and inspect to make sure that those standards have been met. In California, the enforcement is delegated to third-party special inspectors called HERS raters. And the HERS raters are required to follow certain protocols so that the precise way that they go about doing their inspection and verification come from an Energy Commission publication called the Reference Appendices, and it's Reference Appendix Section RA 3.5, and we refer to those as the protocols. Next slide. So why the fuss? Why is this such a big deal? Well, first of all, the the reason we have QII is back in 2005, or prior to the 2005 code, the Energy Commission did a big study, and they had some really smart people. There was people from Lawrence Berkeley Lab and Rick Chitwood and all the big names in the building science world participated in this study, and they looked at a whole bunch of brand new houses. These were like models, sales models of production homes. These are some brand new custom homes, a few spec homes they did. But they went around and they looked at these homes as they were being built, and then after they were built, they did some very sophisticated tests on them. They did some tracer gas studies, they did infrared cameras, and they did all kinds of thermal transmission studies. And basically what they found is that poor quality insulation was very common and very bad, much worse than they expected and much more widespread than they expected. And they determined that on average, the installation was so poor that it actually derated the R value of the insulation by about 13.5%. So what they did is they said, okay, well, if that's basically industry standard, if insulation is being installed so poorly, the compliance software that we use to model homes to demonstrate compliance to the energy code, we're going to automatically derate that insulation because we just know it's installed poorly. And so obviously, you know, the insulation manufacturers, the insulation installers, basically say, hey, wait a second, that's not fair. How do you know, we're guilty until proven innocent. You at least need to give us the chance to do a better job. And so what they did is they came up with a, they call it QII, and it's essentially, a little checkbox in the software. And if you check that box, it removes that 13.5% derating on the R value, but it also triggers the QII inspection protocols, okay? So if they check this little box, they get that 13.5% back, but then other things have to happen during the construction of the house. So there's actually more than one inspection that happens. The HERS rater will go out early in the project to make sure that the walls and the surfaces are properly sealed before the insulation goes in. Then they'll come back after the insulation gets installed to make sure that the insulation itself is installed correctly. And then if it's blown-in ceiling insulation, that has to go in after sheetrock. So the HERS rater will come back and do some inspections. They actually do a test on blown-in ceiling insulation called the cookie cutter test, where they'll weigh it and make sure it's the proper density and the depth and all that good stuff too. Next slide, please. So one of the biggest problems with QII is if it's not planned for from the very beginning, I can guarantee you that there's going to be problems. I get phone calls almost daily from HERS raters out in the field, especially when this first started, when QII first started. I literally was getting several phone calls a day from HERS raters going, what do I do? They sheetrocked over the insulation. What do I do? Well, the answer to that question is it fails. If they cover the insulation up before the HERS rater sees it, if the HERS rater can't see it, they can't pass it, it's an automatic fail. And so we had lots of very upset people out in the field. And we still get those on a fairly regular basis, but word has gotten around because we've been doing a lot of training like this, and we've been training a lot of building departments, and building departments are, building inspectors are a very important, they have a very important role in making sure QII happens as well. So coordination is key. Education of installers is also very important. There's a very high turnover rate for insulation installers, and so they need to constantly be educated. And that's just kind of a role that HERS raters have taken on sort of involuntarily. But most HERS raters, they understand that if they can train the people in advance, they're more than happy usually to go out into the field and walk the project with the insulation installer and point out problems, to walk it with the general contractor, point out potential problems, and you know, educate people in the field so that QII happens correctly. Next slide. So one of the most important things about QII, and one of the most common questions I get is, what is the thermal boundary? And a lot of the questions I get are solved as soon as you can define the thermal boundary. So it's important to realize that the house has to have an insulated shell, and this shell has to contain the air. And if that shell is not continuous all the way around the entire building and air can escape, the insulation is not going to do its job. Insulation doesn't work if air is passing through it. So the first thing you have to do is have an airtight shell, and you have to define exactly what that shell is. And it has to be continuous. It's surprising how many places, like, especially where like the second floor of this house meets the ceiling of the garage, you'll see some rim joists in there. But a lot of times those floor joists go the other direction. They'll run left to right, and there'll be a gap between them. There might be some structural blocking in there, but if they're TJIs, there's going to be little gaps around the side of it. Those all have to be airtight. There's a lot of places. Another good example, as you see in this diagram, is any kind of tub or shower insert that is slid up against an exterior wall. That needs to have some sort of air barrier behind it, okay? And so things like that, you have to define the air barrier, and it has to be continuous all the way around the house. Next slide, please. The other thing is the ceiling of the house has to be the ceiling, C-E-I-L-I-N-G, not S-E-A, ceiling of the house. If it's adjacent to an attic, that is part of your thermal boundary. And, you know, if it's just a flat sheetrock ceiling, that's pretty straightforward. The top plate has to be sealed to the sheetrock, but there's a lot of other places that have to be sealed as well. Any kind of drop ceiling needs to be sealed, needs to have a hard cover on it, as you see in item B here in the diagram. That's a little drop ceiling. They need to put a hard cover over the top of that so insulation doesn't fall down inside that little dropped area, and that hard cover needs to be sealed. Any kind of flue vents need to be sealed. If it's a certain kind of vent, it might need fireproof caulk, and you have to have the insulation, you know, baffle away from it. Any other kind of double walls need to have some sort of top on it, and then any kind of brick or fireplace chimneys, things like that, need to have some sort of shield that makes an airtight barrier, and it needs to be sealed at all those points that you see there. Next slide, please. Any of the top plates, again, if it's adjacent to an unconditioned space, typically an attic, that top plate is part of the air barrier. It is part of the thermal boundary. So any penetrations need to be sealed. Any copper pipe, any waste fence, any wires penetrating there, and then any other holes, knot holes, anything like that, those all need to be caulked and sealed. Sometimes you'll see them drill a hole and then not put anything through it. Still needs to be sealed. That needs to be an airtight boundary. The best way to determine whether or not something needs to be sealed is imagine that the house is under pressure. And if that air from the inside of the house can escape from conditioned space to outside conditioned space, there needs to be some sort of sealed air barrier around it. Next slide, please. Another very common source of leakage are any of the many numerous kinds of penetrations that you see in the ceiling. So any kind of exhaust fans in the bathrooms and kitchens, electrical boxes for ceiling fans, for light fixtures, fire sprinklers sometimes need to be sealed. I'll get back to fire sprinklers in just a second. Register boots in the ceiling need to be sealed as well. So fire sprinklers, there was a lot of debate over the best way to do that. Some fire sprinkler manufacturers said you cannot seal around the fire sprinkler. And so the Energy Commission proposed putting these little boxes up in the attic and sealing those. But some fire sprinkler manufacturers said you can't even do that because some of them need airflow to move past the sprinkler in order for it to work correctly, in order for it to trigger. So basically what we've determined at this point is whatever the fire sprinkler manufacturer says, just defer to the manufacturer's recommendations for air sealing around that fire sprinkler. And the HERS rater, if they inspect a house that has fire sprinklers, they will ask for those instructions on how to do that. Okay, next slide, please. The other thing that's very important is any vertical surface, any wall, including knee walls in an attic, including skylight wells, any vertical surface needs to have an air barrier on both sides. And if it's a 2x6 wall or less, the insulation needs to be in contact with that air barrier on all sides. And the reason for that is if you, on the diagram on the left, if the sheetrock there on the right-hand side, if that's not there, you'll get these thermal siphons where the air will rise on the warm side and then other air will replace it at the bottom. You'll actually get these thermal siphons inside the insulation. If you put that sheetrock on there, but don't have it in contact with the air barrier, those thermal siphons will still happen. And so in order to stop those, in order to reduce them as much as possible, that sheetrock needs to be in contact on both sides, just like you see in the right-hand diagram. Next slide. And you'll hear me say six-sided contact. And in the protocols and in QII documents, you'll see this mentioned a lot, six-sided contact. And basically what that's referring to is that most stud bays and floor joist bays and things like that have six sides to it. So a cube, a dice has six sides on it. And so it's the front, the back, the left, the right, and the top and the bottom. And so for any vertical surface, it must have six-sided contact. On horizontal surfaces, it needs to be five-sided. You can have one side not be covered like that. But on any walls, six-sided contact. Next slide. A lot of times, stud bays have a lot of different kinds of obstructions in them. It could be plumbing, it could be wiring, it could be junction boxes and things like that. And the insulation needs to fit around those obstructions. So if you're using fiberglass bats for walls, there's different ways to do it. The upper diagram shows what we call a cut and butt. So you actually cut the insulation and you butt it together at whatever the obstruction is. You might have to tuck it around behind outlet boxes and things like that, but you want to make sure that there's no gaps and no voids. The other way to do it on the lower diagram is what we call delaminating. So if you've ever looked at fiberglass bat insulation, you'll notice that it's in layers, and you can split those layers apart. You can delaminate it. You can put half the insulation behind it and half in front of it. Sometimes it's really, really challenging. There's a lot of wires. We have some great photos later on that show this. And it may take more than just delaminating or cut and butt. You have to be very careful. But the other thing you have to be careful with is not to compress the insulation as well. Next slide, please. The other place that we see a lot of issues is with architectural pop-out. So this is, if you were to slice horizontally through a wall at a window and look down on it, very common to see these framed out architectural bump outs and details that kind of frame a window, give it a little more architectural interest looking at it from the front. Those, again, the key is to define your air barrier. And you'll notice in the top diagram, this is probably the most common way and probably the better way to do it, is to have the inside wall be defined as the air barrier, the thermal boundary. And you'll notice, if you look very closely at that diagram, you'll see that there's sheetrock on both sides of that insulation at that pop out. The middle diagram shows an alternative method, probably a lot more work though, is to follow the exterior wall and have that be your thermal boundary. And then the third diagram, the final option is just completely fill it. If you completely fill that, you don't have to have air barrier on those interior walls. Both sides of that pop out become the thermal boundary itself. So again, it's just defining the thermal boundary is key. Next slide. So the other thing is full width bats. If you go walk through Home Depot or Lowe's and look at the insulation aisle, you'll notice that insulation comes in either 22.5 inch or 24 inch wide. You need it to be full width so that it expands over and touches each other, as you see in the lower left-hand diagram and not in the upper left-hand diagram. If it's a 22.5 inch bat, the gaps will stay there and they won't touch, and that'll be a fail. The HERS rater will fail that. On floor joists, floor insulation, the insulation in the top diagram would fail because it's not in contact with the floor, the subfloor itself. Or in the middle diagram, if it's not full width bats, it won't expand out and fill the voids of the TJIs. And so the bottom diagram is what we want to see and what the HERS rater will check for. They'll actually put their hands up in there and feel around and make sure that that insulation is in contact on all sides. Next slide, please. Another thing we found is that it is almost impossible to pass QII if you have roof insulation using bats and it has trusses. Okay, trusses are the pre-manufactured trusses with the diagonal truss members. Those truss members will separate the insulation and make it very difficult to have the requirement of no gaps and no voids. If you look on the right-hand diagram and you see those little triangular shaped gaps, those gaps actually go all the way down to the bottom core of the truss and allows air to move through there. So it's very, very difficult to use bat insulation in a truss ceiling and get it to pass QII. We recommend that you use blown-in insulation or some other type of insulation when you have trusses. Next slide, please. So what's different for the 2019 code? So we're currently in the 2019 code. It's effective January 1st of this year. It's based on the permit submittal date. The biggest change is that QII is a prescriptive measure. And what that means is it's on the standard house. The house that you're being compared to has QII. In the prior codes, QII was like an extra credit. You could do it for, if you needed extra credit to pass the code, you could voluntarily choose to do QII. Now it's on the house that you're being compared to. And if you say, I don't want to do QII, you've just dug yourself a big hole. And now you have to replace that energy savings with some other measure. And QII is a hard thing to replace. Okay, it's a big credit. Let me put it that way. Next slide. So the bottom line is QII for the 2019 code will be a lot more common. It has the highest fail rate of any HERS inspection. There's about, I don't know, 15 or 20 different HERS inspections that HERS raters do. Of all those inspections, QII has the highest fail rate of them all. The biggest problems are there's added costs. It requires a lot more time and attention to install the installation, so your labor costs go up. There's a lack of knowledge of the requirements for QII. The design of the house has to take QII into consideration. You can't just apply QII to any old design. You have to take special consideration, the way the house is, the walls are laid out. You need some extra details and things like that. And then the other thing is very tricky coordination with the HERS rater. There's a very small window of opportunity to get the HERS rater in there to do their inspections without slowing things down. Next slide. So tips for builders: know early if the project needs QII. Look at the CF1R Perf 01. That's the certificate of compliance. It's usually in the plan set. On the second or third page, there's a list of all the HERS measures, and it'll say quality insulation on there. So know early. Evaluate the plans very carefully. Look for unclear parts for thermal boundaries, knee walls, hard covers, bump outs, things like that. Fireplaces are a big deal. Clearly define the responsibilities for the trades. You saw all those penetrations in the ceiling. You need to know who is going to take care of those, okay? Clearly define the responsibilities for all of the trades, not just the HVAC contractor, but anyone who has anything to do with the air barrier. Make sure they know what they're doing. Otherwise, there's gonna be finger pointing out in the field. They were supposed to seal that. No, they were supposed to seal that. And then contact the HERS rater as early as possible. Ask them for their checklist, have them meet at the project and do a walkthrough, and then learn to use the CalCerts registry or any of the HERS registries. Learn to use those because there's going to be some forms that need to be filled out. Next slide. And then we have a very nice reference document. It's called the CalCerts QII Handbook. It's basically the protocols with lots of pictures and diagrams. It is not code language, but it is based on code language. It has been updated for the 2019 code, and you can download it from the CalCerts website. Next slide. At the very end of the QII handbook, there are some checklists there. There's one called the ENV21 and the ENV22. Those are the forms that the HERS rater has to fill out. So it's very good if the installer is using the same checklist that the HERS rater is using. And we recommend that building inspectors get used to these checklists too. And maybe while they're out doing their inspection, they can point out a few things and say, hey, the HERS rater is going to catch you on that. The HERS rater is going to catch you on that. Okay. There's also, the CF1R is a pretty tricky document to read, especially for installation and stuff like that. So we have a little guide in the handbook about how to read the installation requirements on a CF1R Perf 01. Next slide. And then the CEC has a hotline. If you have any questions about QII, be sure to contact if you have general questions about stuff, energy code, contact the CEC. Next slide. And then if you have special questions about HERS measures, QII, anything like that, feel free to contact us here at CalCerts, support at CalCerts, www.calcerts.com, and there's our phone number as well. And I think that's the last slide. Yep.
Okay, thank you, Russ. That was excellent technical information. And so for some of you that joined a little later, I want you to know that the webinar is being recorded, so you'll have access to it later. And please put your questions in the Q&A. We're going to try to save a little time to answer those. Q&A on the bottom. And watch out for our upcoming webinars throughout the year. So now we're going to hear from Rich Williams and Jeff Adams from Alliance Green Builders. And take it away, Rich.
Thanks very much, Lynn. Okay, good afternoon, folks. We're going to talk about the importance of air sealing, how the California Code is requiring it, and how to achieve it. Next slide, please. So we're already insulating. Why is air sealing so important? Well, Russ, in his previous presentation, touched on the importance of having the air barrier to have insulation be effective for its R value, it is absolutely crucial that we air seal in our buildings if we want to get the effective R value. Martin Holliday, who's senior editor of Green Building Advisor, some of you may have heard of him, well-respected building scientist, argues that air sealing is actually more important than insulating. So eventually, we've had code requirements for insulating since '78 here in California. And we wouldn't dream of not insulating our homes eventually, and I don't think very far from now, we wouldn't dream of not air sealing our homes properly as well. Next slide, please. So why is it so important to air seal? So 20 to 40% of thermal losses in buildings are from air leakage. That's kind of an astounding value there, because we don't think of air leakage being an energy transport mechanism, but indeed it is. And as again, Russ pointed out, for insulation to be effective, we have to have an effective air barrier to the building. So as we all know, California is trying to achieve net zero, and we cannot do that without properly air sealing our buildings and testing it the same way we test for QII verification. We will be doing the same thing for air sealing ultimately. More than just energy efficiency, we've learned in our buildings that the homes that we do where we properly air seal, it's far more comfortable for our occupants. We couple that with balanced ventilation, so we have improved indoor air quality. That's not really been on people's radar, indoor air quality, but I think it is more so now, given everything that's going on in our states. As of January 2020, currently, we were talking about QII being part of the prescriptive pathway. So the assumption is being made that you're doing QII. But for an energy credit, you can actually take the air infiltration. So you can do air sealing in the Title 24, and you get a significant bump on that. And coupling that with balanced ventilation, it's a huge bump. I've been told that builders, if they have to choose between QII and air sealing, they would rather do air sealing than QII. As Russ pointed out, it's a big failure problem there too. Next slide, please. So a little building science here. So in the building envelope, we have 4 different layers. Bulk moisture control, that's keeping water out of our building assemblies, house wraps, flashing, that type of thing. Airflow control, so we have an air barrier. Thermal flow control, obviously insulation, and also thermal bypasses where energy can transport through building assemblies, like a steel member going from inside to outside. And then a vapor control layer too. So that's really the lowest perm rating you have for a particular building assembly. For example, OSB is a very effective vapor control layer. Next slide, please. So these last 3, actually the whole portion of this is mitigating risk through our building assembly. And the last 3 are part of the complete thermal enclosure system. Next slide, please. So in our thermal enclosure system, we are looking at air sealing, reduced thermal bridging, advanced insulation, QII being an important component of that, and then all the improvements we've seen in fenestration with window U values and solar heat gain coefficients as well. Next slide, please. So getting back to the continuous air barrier, Jeff's going to take over and talk about this a little bit.
Well, just as Russ talked about defining your thermal barrier, you want to define, same thing goes for your air barrier. You want to define it. Think of a balloon. It needs to be continuous, just like the thermal barrier, and completely think about it ahead of time so that you don't have open gaps in it later. It'll be harder to seal. So next slide, please. Next, please. There we go. This drawing here, I don't have a pointer, but if you look at the bottom there on the right, the double framed wall, we did the air barrier on the outside. You can see kind of a dark orange line it's defined coming up and over to the window, and then above the window, up the wall, and then underneath the SIPS panel. We air sealed it before that SIPS panel went on top. The SIPS panel added to our insulation value, and it also provided structural integrity for the overhangs where we have eaves. when we first framed it, there's no eaves in it, and so we can get this continuous air barrier. And I'll show you that on some slides here. Next slide, please. So I even hear this from architects sometimes. Oh, I thought homes need to breathe. Well, they don't need to breathe. People need to breathe. A home that breathes has uncontrolled ventilation. You want to control your ventilation. You know, uncontrolled will bring in moisture and cause problems in your assembly of the walls.
You got to forward here.
Click forward, please. So the homes need to dry, not breathe. Homes that breathe are homes that get moisture in their assemblies, like I just mentioned. Yeah, then they cause problems, and then people can't breathe. Next slide, please. So here's three main driving forces of airflow and heat loss. And starting from the left, it's pretty straightforward. You get winds on one side pushing air in and causing air to go out, negative pressure on the other side. In the middle, the stack effect, we all know that warm air rises up. So warm air will, if you have a leaky house, will leak out the bottom, which cause negative pressures at the bottom and bring air in. One that we don't always think about, though, on the right there, where you have that situation is your ducting for FAU furnace is in an unconditioned space. It's in a ventilated attic. Well, if those ducts leak, which a lot of them do, we find in existing homes, most of them do leak, you're taking air out of the house. You're taking more air out of the house than you're back in. It's leaking out into that ventilated attic, and so that causes negative for air leaking flow. Next slide, please. So the usual suspects, you know, it's all pretty straightforward. Your sill plates and around your windows and so forth. Any kind of penetration in that balloon envelope is you want to get sealed up. You got plumbing, you got wires, and like Russ talked about, you got recessed lights and the ceilings, and like in the second floor there. That's why we actually like to do unvented attics where we take that thermal envelope up on the roof up there instead of on the ceiling. That way your ducting can be in conditioned space and you don't have to seal all around those recessed lights. Sometimes odd framing, cantilevers and knee walls you have to watch out for. So next, please. Next slide, please. Yeah, so then who owns the holes? You know, you have an electrician, back up just a little bit. Electrician makes a hole, the plumber makes a hole, and so forth. So who owns them? They just go on down the line. Well, the person that owns it's the general contractor. You want to watch it and nip it in the bud as it's going. Next, please.
So we talked about, you know, buildings need to breathe to keep out moisture. In fact, it's the other way around. Air transports vast amounts of moisture into the building assemblies. So that's one reason you want to get rid of it. Now building assemblies, they do need to dry out. So if they do get wet, so that's all vapor transport. But this slide indicates just how much moisture gets into a building assembly with a 1-inch hole here. So it's pretty good demonstration in this graphic. Next slide, please. So what's in the code for air sealing? We've adopted in California the 2018 International Energy Conservation Code. I think it's since, oh boy, in the year, geez, I think it was 2013 or something or other. I think that they included air tightness in that. But for some reason, the energy code in California has not adopted the air tightness mandate as part of the IECC. It's kind of crazy. I still haven't figured out why that is the case. But, you know, the writing's on the wall. Eventually, we are going to have an air tightness mandate here. Even Texas and Nevada have an air tightness mandate. And so currently, we just have it in the modeling to encourage it. But one of these code cycles, we will have air tightness and blower door testing as part of our system of getting our homes more energy efficient. And so let's see what else we do. Actually, that's for single family. We don't have a mandate, but we are seeing it in low-rise multifamily, and we'll move on to that. Next slide, please. So we're in, as you can see in the IECC climate zone map, we're in climate zone 3 down here in San Diego. Next slide, please. You might have to click forward a couple times since I have no control here. So there we go. Great. Okay. So in 2012, here it is that we did, ICC code did require blow order test to prove compliance to get under 7 air changes per hour, 50 pascals. Currently, let's see, in 2012 for climate zone 3, it was 3 ACH 50, 3 pascals at ACH 50. So that's what we really should be doing. That's what should be in the energy code, but it's not there yet. Next slide, please. So 2018, again, here we're down in climate zone 3. That's below 3 ACH 50 or below. Next slide, please. So low-rise multifamily. So this is a big one that's come up this year. So as of January 1st of this year, anything that goes in for permitting is going to require either balanced ventilation, meaning heat recovery ventilation or energy recovery ventilation, or a continuous or you actually have to have air tightness verified in the building, and it's arguable that making the units more airtight is a lot more cost effective and easier than putting in a whole nother component of balanced ventilation. And then we talked also already about the single family. We're probably going to see a lot more Title 24s, including air sealing the requirements. So as well as looking for QII, we need to look at that in our Title 24 to see if an air infiltration credit has been taken by a Title 24 engineer. Next slide, please.
So, okay, we talked about the importance of it, but how do we actually do it in the field? And we'll run through a couple of systems here. Next slide, please. Manually air sealing the envelope. You go around and you look for holes, and you foam around your boxes there and foam around where the wires go through, and you caulk joints and things. And you need to do that on the large openings and find those openings that you can see. The problem is this is pretty labor intensive and it's hard. The small leaks you absolutely cannot find. I've come to find out. We've gone through and sealed houses this several 4-man team for a full day. And I look at that and get ready to fire up a blower door, and I go, boy, this is going to be a really tight house. Lo and behold, it's like an 8 or a 10 or a 13 ACH. You just can't see all the small little things that are invisible to see. Next, please. This is one that's really easy to do, very inexpensive, and it's without it, sealing it or caulking it or sealing here with the foam, there definitely will be an air leak at that plate line. And so this is one you don't see a lot of people doing, but it's so simple to do, and it's one of the big suspects. Next, please. Here they came out with zip sheeting. You don't see that a lot out here because it's not available on the West Coast. You have to special order it, and it's pretty expensive and labor intensive. And they tape the seam. You put a tape on all those seams of those sheathings, but it has to be installed correctly, just proper, or else that tape won't stick, and in time it'll peel off. Next, please. There's foam wraps, and on the outside they're pretty good system for sealing the walls. They don't get your eaves in different types of places where strange configuration of framing and so forth. It's strictly the walls, and it's very expensive, and it requires an educated installer. Next, please. There's the liquid applied membranes like Soco we've used, and it goes on as a liquid and dries, and it becomes a bulk moisture barrier and also an air barrier, and it's a pretty good system. It works really nice in a lot of areas, and but you have to go around that whole, think again, that balloon, you have to follow that air barrier, continuous air barrier on the whole house, and it takes a lot of time to put this on, and it's pretty expensive. Next slide, please. This is the one I showed you the diagram when we defined the thermal envelope. Up in the upper left, we haven't put those SIPS panels on yet. And during construction, the same product, but they changed colors of it. So it made for a funny looking building there. But on the left there up above, you can see where we put it on the first time. And we first time this installer had done it, we went back and patched up some little teeny holes we could see. And it made for funny looking too. But there you see it comes up the walls and over the ceiling, I mean the roof, all in a continuous form. Then on the right, top right, where you can see we added some overhangs where the walkways are outside, that went on after that air barrier. Lower left, you can see the SIPS panels going on top of that Prosoco product. And on the right, you can see all the SIPS panels on. And it's already been airtight and continuously. Next, please. Closed cell foam works pretty well. Seals up pretty good, but not 100% effective. And it's this is the raised floor foundation where we sealed underneath there. That's our continuous air barrier right under there. And there's some concerns that it off-gas pretty quickly. The next day it seems to be fine, but now scientists are starting to wonder if there isn't still some small off-gassing over time. Next, please. There's closed cell foam, works pretty well too. It's less expensive than the closed cell, but it's still pretty expensive, and it's not 100% effective. Next, please.
So as you can see, around the block trying to figure out how to air seal our projects here, and then the company AeroSeal came out with a product for whole homes. AeroSeal is a duct sealant system, and they came out with AeroBarrier. So this is turned into our silver bullet sealing. It'll seal up to ½ an inch and down to a size of a human hair. So we go around and we seal all the major cracks and openings we can see with gun foam, and then we use AeroBarrier to seal the rest. As Jeff pointed out, most of the holes seem to be smaller ones. Air leakage seems to be death by 1,000 cuts. It's remarkable just how many small little holes that you can't see add up to a lot of air leakage. So we've been having a lot of fun with this, and I don't know if any of you have heard of Passive House, but we can consistently get down to Passive House level of air sealing with this. And I think within 5 years or so, you're going to see the majority of homes utilizing AeroBarrier for air sealing. It's just so much more cost effective and time saving. So next slide, please. So what we do is essentially pressurize the house, and we pump a aerosolized sealant into there, and it's like Fix-A-Flat for a house. It accelerates towards the openings and it just adheres to the sides of those openings and creates a caulk sealant over those. Next slide, please. Here's an example. Those are nozzles that are carrying sealant in tubes as well as pressurized air, creating that fog you can see in the upper right hand side there. Down the lower left, you can see the operator there with the blower door is how we pressurize the home, and actually pressurize it up to 100 Pascal, so double the testing level. And on the bottom right, you can see an example of where you have two framing members where there was a huge leakage point, and the sealant has gone into that and sealed that up. Next slide, please. On the left-hand side there, you can see where that penetration is right there on the OSB. The exterior sheathing is sealed around there. We can do it at the exterior sheathing or at the drywall level too. You can see, for example, in the top right here around that electrical box where between the drywall and the electrical box, it seals there, as well as in the back of the electrical box where the wires are all coming through. So those are just examples you can see throughout this slide here of all the different areas that it can seal so easily. Next slide, please. So the software actually regulates the process. It monitors indoor humidity and temperature, and it has very careful sealing there. And we verify the results, which is wonderful for folks. It makes it very easy. There's no guesswork in this. Next slide, please. So there's an example right there of a sealing certificate that we provide. So there's a good example from a home in Solana Beach here. Oh, you can go back to the back of my slide there. Okay, so this one started off at 11 ACH after going around with gun foam, and we finished down below passive house levels of 0.5 for air changes per hour in about 80 minutes. Pretty remarkable to be able to do this. But this is the nice thing is that you don't have to, with air sealing and air barrier, you don't have to test it and then have somebody come back and seal it. It's all verified, a certificate provided, and it's a lot easier than QII for sure. Next slide, please. Next one. Okay, that's it for us. We can keep the questions till the end, as Len said. On to you, Danny.
Thank you, Rich and Jeff. That was very interesting, and sounds like air sealing is gaining popularity and will be part of our California code pretty soon. So now we're going to hear from Danny about all the kinds of insulation. Go ahead, Danny.
Thank you, Lynn. My name is Danny O'Connell with Next Level Insulation. I've been in the insulation industry for about 30 years and been in construction most of my life prior to that. And I have some slides here. And one of the things that Russ brought up, and I think Rich brought up as well, or Jeff, that you got to let the builder and the other trades get involved early. It's just so important because there's going to be extended cost to them, and that it's unfair to them to have to come into this. So once they start doing it, they'll absorb those costs, and it'll be just in the cost of the house. It's kind of like seatbelts in the 60s. It was an option. Now seatbelts aren't. So they just have to be able to do that. You can go to the next slide. This is what I call bad bays, or just, it's kind of hard to insulate that bay with all those wires in it. You know, one of the things Russ was talking about was the laminating bat. But one of the things you could maybe do is find those places early, and maybe before the electrician or whatever goes in there, you could put a piece of rigid back in behind there, and that would fill in that cavity. And it would just be easier to get the insulation value that you want in that cavity. But, you know, a lot of times the bays are just completely full with everything. It's how are you going to get a bat in there? Go to the next slide. Again, these are some bad bays. There's just a lot in there. How are you supposed to insulate? Next slide. The air infiltration thing. This is a house they took the drywall off as a remodel. And look how dirty those bats are. So obviously air was getting through. The air is coming into the house. So it's not just for thermal. Obviously the air infiltration properties of air barrier and insulation is going to allow to have air quality in your house. That would be much better. So we ended up taking all these out and re-insulating all the houses. Next slide. This is a bad insulation job. All these bats have gaps and voids. That's where the air is coming through, the dirt, the dust, the noise. They didn't do laminating to these bats. So where you want it to, the body of the bat tends not to have a problem. It's around any structure. The bats are 16, 24 on center. If the bay is 12, it's got to be cut. It's when the human cuts it. Those gaps and voids, thermal, sound, and teenagers do the same thing. They take the path of least resistance. So they're going to, you know, the sound's going to come through, the thermal's going to come through, the dust is going to come through. You can go to the next slide. Here's just some pictures of some bad bats just kind of thrown in from the ground, poked up with a stick. We try to have our guys always do the bats by hand. They can, like the walls, up in the lid as well, and then you can get a bat much more non-compression, non-gaps, non-voids. Next slide. Again, there's some more here up in the ceiling, and it's just really going to degrade the R value of the bat, the air infiltration properties of it, and it's just not a quality installation job. Next slide. And these are just some pictures I did of a good bat job. It's never going to be perfect with a fiberglass bat. It's just tough to work with, especially since most cavities aren't 16 or 24 because of the layout. So just try to get it as much as possibly that you have the bat. Just having all 6 side contact, like Russ had mentioned. We don't control the 6 side, which is slide right into place. So we only can control 5 of the 6 sides, but that's another. Next slide, please. I think there's some more pictures of good bats. Yeah. So as you can see, we just try to get it in there and just try to not have compression, delaminate the bats around the wires, boxes, can lights, things like that. Next slide. There's just some other pictures of bats that are installed. It takes a little bit of time to train the guys, to train the builders, and to train the other subs. Just to kind of, everybody has to buy in. It just has to be done early, and they have to buy in. This is open cell phone, and the problem with this, it has those gaps and voids as well. So whether he was moving too fast or the heat wasn't right, but open cell foam isn't cheap, and if you're not going to get a good job and you're using a higher end product, you just wasted your money. So you're still going to have those gaps and voids in those areas up against the perimeter of each bay. Next slide, please. Again, these are the same things. It's open cell foam. There's some gaps and voids. Air's going to slide through, and you're not going to be happy with your insulation job. It's going to come through. So, next slide, please. This is the open cell foam, good job of it. It comes out past the studs a little bit, and then you shave it off. See that picture on the left? And then the picture on the right is what the cavity would look like after it gets shaved off. And it's full, 5 sides, 6 sides by the drywall, and you're just going to have each cavity just being filled to its minimum or its maximum of the R value and also the air filtration properties. Next slide. This is closed cell foam, and this is very, very expensive. But you can do just 2 inches. After 2 inches of closed cell foam, you're really doing nothing but paying for the value very expensively. So you can do what's called a combo or a hybrid, and so you can put a fiberglass bat or you can net pump cellulose in the rest of the cavity to get the remainder of the R value in the cavity. 2 inches of seal is just really, really good. When it's sprayed in about 5 minutes, it's hard as a surfboard. It is just really rigid. And you can do it as a prelim prior to maybe framing inspection, get it up in there, and then later on put a bat and or cellulose or another product in the remainder of the cavity to get the remainder of the R value. Next slide, please. This is a product that we've been using for about 1.5 years, 2 years, and it is made out of sheep's wool, and it is a little bit heavy, so you have to staple it in. So we kind of get the perimeter of the bat handled and the air filtration properties of it because we're stapling it because it's kind of heavy. And it is a pretty amazing bat. I think the product, what it gives the sheep in nature, it kind of gives your house. There seems to be a moisture wicking ability to it. The air filtration properties, the sound. It's a pretty dense bat. It's a bat we've been pretty excited about. We've been doing quite a bit of it lately. Next slide. This is a little product, and you can put it in anywhere that you can put any other kind of insulation. It's a little bit tough to work with, a little bit tough to cut, but the sound quality and the thermal quality are quite exceptional. Next slide. This is one that is kind of close to my heart. I've been doing this product actually for about 30 years, and it's spray applied cellulose. It's recycled newspaper. We spray it in, for lack of a better term, kind of like a spitball, but it's not very wet. It's a light mist that we put on it. The starch is in the bag, and then it slams up against the outside building material. We do it on interior walls. We put a netting that's not unlike the netting that's on your mattress or under your couch. We put that on one side, and we spray into that, and then we screed it off flush. So you get those 5 sides that Russ was talking about, the 6. Of course, we can't affect the 6 because it's drywall. But because we're flush in the cavity, and what I like about, say, spray applied cellulose as opposed to a bit, which is a blown-in blanket with fiberglass, is that you're actually attaching it to those 5 sides with that starch. So the velocity of which it hits the wall, and then it gets scrubbed off, and then it actually attaches. And next slide, please. gaps, voids, boxes, wires, all the things that might be in the cabinets. Next slide. This is one, I think the one in the middle I can see, or actually all three of them. What we did there on the lid was we actually sprayed 2 inches of closed cell foam, and then we netted with that netting I mentioned. That's kind of like the one under your mattress. And we netted it and pumped cellulose into the rest of the cabinet. We sprayed that, we pumped that in dry, and it just fills all those, the cavity perfectly. It's great for sound. And then again, there's spray flex cellulose on the exterior walls and the interior walls as well. This was actually a house that we did for Rich and Jeff 3 or 4 months ago. Next slide. And that's about it. One of the key things I think is, and both other guys, I guess, mentioned it, you got to get the builder in early. You got to get them an inspector, walk the inspector. It's mostly going to be the framer that you're going to be working with to get everything dialed in, but the AC guy, electrician, plumber, they're going to be involved as well. Thank you very much.
Okay, thank you, Dan. Looks like there are a lot of choices.
Yes, there are. Questions?
It looks like there's a lot of choices in insulation.
Yeah, there are.
Are you speaking?
Can you hear me?
Okay, here I am again.
Nope. Yeah, there are a lot of choices.
So we have a few minutes left, and we have a couple of questions. Actually, we have one question here. I think I'll just read it. Although there's a little echo, Yasmin. So HRVs and ERVs operate differently. Why is the option of either applicable here in San Diego? Russ or Rich?
This is Russ. I can answer that. So they were mentioned as part of the balanced ventilation for multifamily homes, and the point is that they're supplying the same amount of air that they're extracting, and so you get a neutral pressure created in the house. If you choose not to do that type of ventilation, either ERV or HRV, the requirement is that you have a really, really tight shell so that the multifamily units don't share air with each other. And then you have to do a blower door test to test those. That's what that was mentioned in this presentation. As far as the difference between an ERV and HRV, it doesn't really matter too much to the energy code because they'll both be rated with an efficiency. And the energy code is just looking at energy recovery. HRVs will also do energy recovery, and so they're both. As far as the application goes, I'm actually not sure, which is better for certain climates. I know one works better in a humid climate than others, but as far as the energy code goes, it doesn't matter.
And Rich, what's your opinion about working with those down here in San Diego?
Well, as builders, it's probably one of our greatest hurdles to advise our clients to add that to the scope of their project, because people say, why would we need a ventilation system? We just keep our doors and windows open, which we've actually found is not necessarily the case in practice. You use either windows for ventilation or for cooling. And I can tell you, Rusty said, what's better, HRVs or ERVs? That's a question that we've been wondering because we have such a temperate climate here. We've just settled now, just use ERVs across the board. And now, especially as we're getting more and more humid summers, it's definitely better to have the ERV than an HRV. So you're not dealing with all that latent heat and moisture too in the cooling season. But in practice, we found that you either have to, we're required to do ventilation anyway for ASHRAE as part of code. So typically we use two-speed bath fans, but if you're doing a tight envelope, the two-speed bath fan is trying to suck makeup air through the building envelope, which is not an effective way of doing it. So to have correct ventilation, we really do need to put balanced ventilation in. You don't have to put an ERV or an HRV in, but why not do that? Because it's just a simpler way of doing it than trying to do some makeup air system, which we've also done too.
Tastes better.
And it does. I mean, I think really, you're bringing fresh filtered air into your home. The homes that we've built where we've had ERVs, it's way nicer inside the house as far as indoor air quality and the way it feels than outside. And that's what homes are supposed to be. They're supposed to be shelter, protection for us. So it should be better inside than outside. That's typically not the case in the homes. They're usually indoor air quality inside is worse than outside.
Okay, thanks. And George says he thinks that the ERV is correct. So we're right up against our time, but we have one more question here. The best sealant for air sealing from interior for multiple materials, for example, drywall, metal, wood, etc. What do you think, Rich?
From interior for multiple materials, drywall, metal, wood. Well, as we've said, I mean, you can go through. This is a rabbit hole you can go down here. I mean, in between, say, electrical box and drywall, well, you want to walk around and do that with caulk. Spray foam is going to make a mess. It all depends on where it is. Typically, we go around with gun foam and do as much as we can there. At the drywall level, you have to use caulk. But again, I would just use aero barrier. Get the big holes with gun foam and then just use aero barrier because it's a lot more cost effective. There's just so much you don't see doing things manually. As far as the best spray foam, we like the Dow Pro Seal gun foam that's you can just get at Home Depot. They've got great gun foam. They're with not the kind with the plastic straws, but the one that goes with a gun. It's about $50 or something or other for a gun, and then it's can screws onto that, and that stuff works great.
Okay, thanks. And so, Yasmin, we have a couple more questions. Do you want to cut us off, or what do you say?
We can get back to those people who asked the questions. If you guys want, it's up to you.
Okay, there are just a couple of questions about spray foam from Chad, about the closed cell spray foam cost per square foot, and what's the best spray foam for air sealing cracks.
Danny's probably the best person to answer.
Closed cell foam is probably going to get you your best seal and give you a big bump on your R value. Say if you had a small cavity, say you had 2x6 up in Raptors, and that's where you want to spray the roof deck. You almost have to use closed cell foam because it has almost 7 Rs per inch. So it all depends on the cavity. It really does. So it's really hard to price unless you walk the whole house. But closed cell foam is the most expensive. Open cell foam would be a little bit less. Cellulose, blown-in blanket, like I mentioned, which would be netted and then pumped with either fiberglass or cellulose, and then bats would be next. But it's really hard to give you a square foot price. Best thing is, have an insulator come out and take a look at it and give you a price.
Okay.
Lynn, I see Chad's got a question here. Looks like he's wondering why you have air exchanges and infiltration for apartments. It has to do not with energy efficiency or anything. It has to do with the unit-to-unit transport of pollutants. We got a call from somebody that's got an 1,800 square foot penthouse apartment in Las Vegas, luxury apartment, and his next door neighbor smokes pot all day and cooks curry. And he says, how do I stop this? So he says he spent millions on this thing, and he's got his next door neighbor messing up his entire life. So it's all about either balancing ventilation so you have no pressure differentials between the buildings, or actually sealing so that demising wall gets sealed. So that's what that's about, Chad.
Right, and it is based on ASHRAE, the 62.2 that's in place right now for the energy code. So I guess we better wrap it up, huh, Yasmin? And thank you all
Thanks.
for coming. I want to remind you to look for our other webinars that will be coming up, and we will have one about ventilation. So we'll talk more about ERVs and HRVs then, I'm sure. And I'll give it back to Yasmin.
Everybody for attending. Have a great day.